Good morning. This is Dr. John Whitcomb talking about we've learned how memory happens, a huge leap forward. We've learned the mechanism of it. Actually, we haven't. MIT did, a research team at MIT we're going to report about. And how is memory adjudicated in your brain? Well, just for starters, here's some physiology. You have a couple trillion neurons, maybe a few less neurons, but each one is connected to probably 3,000 to 4,000 other neurons with long filaments, wires called axons. And at their end plate, there's a little foot. That's basically where there are neurotransmitters called a synapse. And the synapse is basically a little place where neurotransmitters have to be excreted across. Now those synapses are made of, their walls are made out of plasmalogen lipids, and they have to be plasmalogen lipids because plasmalogen lipids are the only lipids that are so fragile and so fluid, they allow the little vesicle of neurotransmitter to fuse with the membrane, which allows it then to rapidly excrete its little bit of neurotransmitter across that synapse. So for me to have speech, for you to have vision, for me to have hearing, all of those functions require very rapid transmission of neurological symptoms. So we could not have developed a central nervous system without plasmalogens. All right? And so those synapses are connected to each other and connected to other cells. You have roughly, say, 4,000 synapses per neuron, which makes folks estimate that we have something on the order of 600 to 700 trillion up to 4 quadrillion synapses in your brain. And we reported, this column reported that 6 months ago at Yale University, a novel imaging technique of the brain could show synaptic density. And in their study, they showed that synaptic density was correlated highly with cognitive function. And by testing some 60 volunteers with variable levels of cognitive function, they found a precise correlation with cognitive function and synaptic density. And we know that if you do CT scans on elderly people, the radiologist will say to you, oh, normal brain shrinkage appropriate with aging. That's utter nonsense. There's no such thing as appropriate shrinking. That's because at age 50 we reach peak plasmalogen density, and from 50 to 70 we've lost 20% of our plasmalogens. If we lose plasmalogens, we're losing synapses. And synapses are where memory is mediated. So as best we can tell, a memory is created by, or we're just presuming this, thousands of synapses connected in a very complex way which we haven't learned how to interpret yet. But what we see is the sine qua non of Alzheimer's is a shrunken brain with fewer synapses. And you have so much redundancy and so much resilience and so much overlap that you can get away with losing 20% of your synapses and still have no symptoms, and we call that normal aging. And you just have a senior moment here and there and forget a word or can't remember somebody's name or where are the car keys or where did I put down my coffee cup, all those little irritating things that gradually get worse. And when they gradually get worse, then you start retreating into yourself and stopping engaging and learning new things. Okay, that's what normal Alzheimer's and normal memory is. What was the discovery this week at MIT? What they found was when you look at mouse brains under very high power at one synapse at a time, you find that axons aren't just normal little threads. They have little tiny protrusions on them that are actually immature synapses called philopodia. Oh. And if you actually look at them, they aren't electrically active. You have to have both AMPA and NMDA receptors activated in them. You can do that by putting glutamate and looking at one synapse at a time and seeing if it becomes activated. And these little immature ones aren't activated. And they're roughly 30% of the axon synapses in your brain. So 30% of your synapses or of your connections are immature, waiting to be activated. In other words, waiting for memory to happen and then to be reinforced. So when you take guitar lessons and you learn where to put your fingers on the fret, you forget after a week. If you do it again, you still forget. If you do it a third time, now you start remembering. You do it a fourth time and you cement it, and you keep repeating behavior, and you cement behavior, and you make that little philopodia into a permanent connection. So what we now see is there are many synapses, 70% of them are permanent memories, permanent function that teaches you your function, how to do things, but there's 30% in reserve waiting to be used. And an adage that we see everywhere in your body is use it or lose it, which means you need to keep learning things every day. And in the last couple of years, it's become increasingly obvious that super-agers, people who get to be 90, do just that. Learn something new every day. I'm learning how to do these podcasts. You're learning by listening to me. Stretch yourself every day to do something new, because that's how memory is made. And then watch Goodnow's tapes about plasmalogens. Take the test. Find out how your brain functions. Replace plasmalogens. Learn how to turn on your cells so they make it naturally. Hint, intermittent fasting turns on your peroxisomes where plasmalogens are made. Maybe there's something to it. Maybe we should all be missing breakfast. I haven't eaten yet today. This is Dr. John Whitcomb for News and Nutrition, how memory is made, and you can make yours too.